All right, let's jump right into this explainer and look at how modern engineering is absolutely crushing the universal nemesis of moving parts, friction. I mean, we rely on machinery every single day, right? And wherever there are moving parts, there is this constant, invisible battle against wear and tear. So today, we're unpacking the brilliant solutions engineers have come up with to create components that actually lubricate themselves. It's keeping our industrial world spinning, literally, without a single drop of messy grease.
To get a real feel for this technology, here's our game plan. We'll start with the science of tribology, then move on to the mechanisms of self-lubrication. After that, we'll break down the anatomy of composite bearings, check out homogeneous polymer bearing structures, and wrap it all up with industrial applications and selection. We're going all the way from microscopic physics to massive industrial machines.
Okay, Section 1, the science of tribology. Before we talk about the bearings themselves, we really need to understand the physics of how surfaces interact. Enter tribology. Coined back in 1966, this is the entire scientific field dedicated to friction, lubrication, and wear. The big takeaway here is that friction causes massive energy loss and mechanical wear. Tribologists try to minimize this using a specific system: base bodies, counterfaces, and lubricating layers. Honestly, anytime two surfaces move against each other, this whole system is at play, and if it's not managed properly, the heat and material loss will literally grind a machine to a halt and destroy it. No way around it.
And this brilliantly illustrates the core challenge we're talking about, the Strybeck curve. You'll notice this steep drop where the friction coefficient behaves relative to rotational speed. That plunge happens when the rotational speed kicks up and a fluid film successfully builds up to separate the two sliding partners. So, we're moving from high friction boundary conditions, where it's just metal rubbing on bare metal, through mixed friction, and finally into this ideal state of fluid friction, where the parts don't even touch at all. It's kind of the holy grail for moving parts.
Moving on to Section 2, mechanisms of self-lubrication.
Now, getting that perfect fluid friction usually means you need an external pump continuously forcing oil into the system. But let's look at how a bearing can actually do this itself. No external help required. We start with sintered metal bushings. Picture a rotating shaft inside a bearing made of metal powder that's been pressed into a coarse, sponge-like structure and completely filled with oil. As the shaft spins and heats up from that initial friction, the oil trapped inside those microscopic pores expands and gets forced out to the surface. This creates that crucial hydrodynamic lubricating wedge we just talked about, physically decoupling the bearing from the shaft. And then, this is the real magic, as the machine shuts down and cools off, the metal acts exactly like a sponge. Capillary action literally sucks the oil right back into the pores for the next startup. It's a completely self-contained system. How cool is that?
Section 3, anatomy of composite bearings.
But what if you're working in an environment where you absolutely can't use liquid oil? Well, let's peel away the physical layers of composite dry bearings to see how they pull this off. What's super interesting here is how engineers have stacked highly specialized materials to get the absolute best of both worlds in a 3-layer composite. At the base, you've got a robust metal backing like carbon steel or bronze, which gives the bearing its immense structural strength. This handles the heavy loads and allows for a secure press fit into a housing. In the middle, there's a porous centered bronze layer. This acts as a mechanical anchor, and it's also a fantastic heat sink, pulling damaging heat away from the interface. Finally, that top sliding layer is made of PTFE. You probably know it as Teflon, mixed with some very specific fillers. By combining these 3 distinct layers, engineers get the heavy load integrity of solid steel perfectly paired with the incredibly slick, low-friction PTFE surface.
Which brings up a really fascinating question. How exactly does a completely dry metal polymer bearing lubricate itself? I mean, if there's no liquid oil weeping out of a sponge, what on earth is stopping that metal rotating shaft from just chewing up the bearing surface?
Let's dive into the mechanics because it's an incredibly ingenious chemical and mechanical process. During the initial run-in phase, microscopic amounts of that PTFE mixture are actually sacrificed and transferred directly onto the mating shaft. This wear debris embeds firmly into the metal's microscopic valleys, forming a highly stable, protective transfer film. So after just a brief run-in period, you don't have bare metal rubbing against polymer anymore. Instead, the interface transforms into a remarkably slick PTFE on PTFE sliding action. Basically, the bearing coats the shaft in its own polymer material. And incredibly, that generated wear debris actually acts as a solid, third-body lubricant. It's a real game changer.
All right, Section 4, homogeneous polymer bearing structures.
So that's the layered approach. Let's contrast that with homogeneous polymer plain bearings.
Unlike the thin sacrificial layer we just looked at, these engineered plastics mix the solid lubricant uniformly throughout the entire part. We're talking solid lubricants embedded as tiny, microscopic particles directly into the base polymer compound. Because it's a homogeneous mixture and not stacked layers, the entire wall thickness acts as a consistent wear zone. This means the bearing stubbornly holds onto its low friction characteristics even as it wears down over time. Plus, since it's totally solid, these lubricants can't be washed out by chemicals or easily damaged by dirt and grit. Engineers even throw powerful reinforcing agents into the mix to boost compressive strength, making sure these plastics can take intense edge loads without deforming out of shape. Of course, choosing between traditional metal and these advanced polymers means facing a classic engineering trade-off. Pitted head-to-head, traditional bronze bushings offer massive compressive strength for super heavy machinery, but they absolutely demand a consistent film of grease. If you skip that scheduled maintenance, the resulting metal-on-metal contact will violently fail, causing severe noise and catastrophic damage. On the flip side, PTFE and polymer bushings give you maintenance-free, self-lubricating, and virtually silent operation. The catch is that they're typically best suited for light to moderate loads, just to ensure the plastic doesn't deform or permanently creep under extreme pressure.
And actually, even within the plastics category, you have to choose your materials really carefully. For example, acetal and nylon might look incredibly similar, but they behave very differently depending on where you put them. Acetal absorbs almost zero water. That makes it absolutely perfect for wet, submerged, or highly humid environments where keeping tight dimensional tolerances is critical to the machine's function. Nylon, on the other hand, handles mechanical shock beautifully. It's the go-to for dry, heavily loaded gears and bushings that need to take an absolute beating without shattering.
Finally, Section 5, Industrial Applications and Selection.
So how do all these microscopic principles, solid transfer films, and distinct material properties actually translate into the real-world machines we use every day? Well, it all comes down to the performance metrics. The hard numbers strictly dictate the application. These dry bearings boast a friction coefficient as low as 0.05, which translates to extremely low energy loss without a single drop of grease. They can withstand static loads up to 250 megapascals, meaning they can hold up massive stationary weight without getting crushed. And their operating temperature range? Truly staggering. They run smoothly everywhere from a freezing negative 195 degrees Celsius in deep aerospace vacuums, all the way up to a scorching positive 280 degrees Celsius inside industrial ovens. Because of these incredible specs, you'll find these self-lubricating wonders hidden all over modern industry. In the automotive world, they're heavily used in steering tie rods, where the PTFE debris actually acts to permanently smooth out the ride, and in pedal assemblies, where traditional sticky grease would just attract dirt and eventually fail. In the food and beverage industry, they are absolute lifesavers. They allow for completely sterile processing lines that require frequent chemical washdowns, completely eliminating the ever-present risk of toxic grease contamination. And out in harsh marine environments, bronze-backed metal polymer variants just shrug off aggressive saltwater corrosion entirely, keeping rudders and winches moving freely. This brilliant evolution from messy, high-maintenance grease to self-replenishing oil pores and molecular polymer films proves something pretty profound. The smartest engineering solutions are very often completely invisible to the naked eye. It really leaves you wondering, as materials science continues to rapidly advance, what other frustrating, routine mechanical maintenance tasks are we on the verge of redesigning right out of existence?